Okay, so this is Travis, and it is the 8th of July, and it's just before noon. I took a little bit of time this morning and ran through a design shred for essentially Wildfire design to see what we would be looking at. And then I think there's a bunch of questions here that would be unanswered where we would want to provide some tools to design engineers in order to do this type of design. So first up, I used this sample building to run through some scenarios, and the sample building comes from a PNNL study where they were looking at infiltration rates for buildings, and so they had some, it's kind of nice. Hold on, I'm going to bring it open. This is the study, Infiltration Modeling Guidelines for Commercial Building Energy Analysis. And I think the most important page of it is this one where they talk about the infiltration rates of different types of construction and overall infiltration rates. So anyway, I use that sample building, which comes directly out of the study. And for the mass balance here, what we're basically looking at is you have PM 2.5 coming in from your outdoor air, PM 2.5 coming in from your infiltration. You could have PM 2.5 being generated by internal sources, but right away I'm going to say that, in the scenario of a wildfire, that's negligible, so we're going to count it as zero. And then the only way that we have of removing PM 2.5 is the filters that are actually going on. So to pick some design conditions, I selected 150 micrograms outside and 30 micrograms inside. Convert that to feet because all the other units I'm going to use are in feet. Some people have referred to that as the indoor-outdoor ratio. And so in this case, that would be 20%. If you wanted to try to maintain 30 during a more extreme event where it's like 250 outside, then that would be an even lower ratio. So the first question, of course, is which one of these is the bigger load and what is the overall relative magnitude of those loads? And so for this building, that's not too hard to calculate. If the outside air was at 0.15 CFM a square foot, like for an office building, then you're going to be looking at this 37,000 micrograms a minute as the load coming into the building. As the ventilation rate increases, obviously that'll go up. So for 0.2, more like a school or one of our clinics, it'd be about 50,000. And I'm guessing that if you had, it would just ratchet up from there as your outside air number increases. The infiltration one is the one that has a whole lot more variance. So some of actually this PNNL study talks about a leaky building at about 0.12 CFM per square foot. That's a different square foot, by the way. It's the it's the wall area rather than the floor area. So at that point, you could be looking at 130 micrograms per minute coming into your building, which is a big load. On the other hand, if your building is designed to sort of modern or current energy codes, the building could be quite tight, and that number could be, you look at it, it's an order of magnitude less than what's going on with your outside air loads. So the primary tool for removal is the filters. Let's take a look at filters and just look at how some of the math works around filters. Basically, all the air hitting the filter it has the removal effect of the filter. And so in that sense, return air is important as well as outside air in order to create a removal effect. One way to improve or increase the amount of removal that's happening at the filters is to increase the overall flow through the filters. And I'm sorry that you can't see these. I think I can go to full screen on this screen. No, I can't. Sorry. But we can zoom in on this. But what you'll see here is that, here's your overall indoor concentration. If your outside air is at 150 micrograms a cubic meter and you have 0.15 CFM a square foot of outside air, 0.35 CFM a square foot of total air, well, then you'd wind up at, 115, 120 with your MERV 8, MERV 10, MERV 12 stuff, and you'd be just under 40 with your MERV 14. If you increase your overall ventilation to here's 0.9 CFM a square foot, right? So increase your overall ventilation to 0.9 CFM a square foot. Well, then you're actually doing quite a bit more removal, even with your lower filters. And in a MERV 13, MERV 14 scenario, you're under the target. So you're doing quite well. These other numbers are just if you increase the outside air. So this is outside air at 0.15, this is outside air at 0.2, this is outside air at 0.3. And so in each case, it just ratchets up a little bit. I think maybe the more interesting way of looking at the filters is to look at it in terms of actual removal. So you calculate a load in micrograms per minute, and then you look at what your removal rate is in micrograms per minute. And you can see the numbers here, 10, 20, 30, 40, 50, 60, 70,000. I think to put that in perspective, so this number is wrong, by the way. I'm not going to fix it now, but that should be more like 45. And so this line is in the wrong place. But think about this for like for a leaky building where you have your infiltration load plus your outside air load. You could be looking at 170,000 micrograms a minute coming into the building. Well, your removal rate from the filters is nowhere near that. It's not even half that. On the other hand, for this ASHRAE 90.1 building, if your infiltration load is relatively low, your outside air is normal, then you'd see another number coming into the building. And in some of the MERV, in some of those MERV scenarios, you would actually be keeping up. What is this number? It's 41.5 is what it is. So you can kind of see right about there. You can see what scenarios are keeping up with the load and what scenarios are kind of not keeping up with the load. Okay, so that's filters and removal. There's a lot of conversation, I think, if you are in one of these leaky buildings where you have this tremendous infiltration load, then you are going to want to look at pressure and wind pressure. In order to do that, though, we do have some tools. There are the windrow data that we can pull off of some government sources. And so I think you would do that. Both fires and wind are seasonal. And in a high-rise buildings, you're also going to have stack effect. But I thought it was interesting when you look at windrow data, most of our infiltration studies tend to be based on this 0.3 inches of static pressure, 75 Pascal. And that's quite a bit of wind. Or I guess it's higher than the average that I would expect in some of our territories. It turns out to be about a 25-mile-an-hour gale. 50 pascals is more like a 20-mile-per-hour gale. And so that's I don't know whether or not that's an appropriate design condition. I've never done design for wind effect like this, and so I think that's something that we should definitely address if we want to talk about pressurization. If you were trying to put things in perspective, HEPA filters. So let's say that we were in one of these buildings where we had 150,000 or 170,000 micrograms a minute of load, and you were going to think about putting HEPA filters into the space in order to do some removal. Well, HEPA filters are great. They remove basically everything that hits the surface of them. But 1,000 CFM HEPA filter, it removes more of the dirtier the air in the building gets. So if your air in the building is at 30 micrograms, then every 1,000 CFM you push through a HEPA filter is removing, 850 micrograms. So in order to keep up with the big load like this, to me, that seems unreasonable. You would need to have, I don't know, 150 of these HEPA filter units sitting in the building or some other strategy like that. So anyway, that was a design thread I came up with for the morning. I think in this design guide, if we're going to issue a design guide, what we need to be doing is we need to be giving engineers the tools and the frameworks to be able to select options. I very much think that it's incorrect to try to come up with just standard solutions and one-size-fits-all options. The most important thing that's going to need to happen is to determine, okay, what is your load? Are you in a leaky building where you have this kind of load? Are you in a massive outside air building, maybe a hospital, where that's your load? What is your primary load? How are you actually going to put removal in place to deal with that primary load? Do you have it on a normal basis? Do you need to do it on a temporary basis? If you do it on a temporary basis, what's the capacity of the removal that you're capable of putting in? And we need those kind of tools. So those are my thoughts on wildfire design.